Today in class we looked at the cause of friction. We said that the force of friction is something that opposes motion, and where it comes from is what we call microscopic imperfections in pretty much every surface you see. I mean, you can even see that in your hands, how your hands are not perfectly smooth, they've got ridges. We've got two types of friction that we want to deal with. There's a third type of rolling friction, but we'll deal more with static and kinetic friction in this exploration. What they're trying to show you here is the surfaces of two different objects. You can see the surface of the desk in gray is not perfectly smooth. It's got some hills and valleys, and the surface of the book, or whatever that block is not perfectly smooth. And it's due to those imperfections, that interlocking of those imperfections is where we get friction. Here is a picture of zoomed in paper down, you can see, to micrometers range. And you can see that a smooth piece of paper that you might be writing on right now actually has tons of hills and valleys all over it. It's not perfectly smooth. So what we want to look here is the exploration of what causes friction, what friction actually depends on. In the shoe lab, you guys figured out, or more force of gravity, it seemed like there was more friction. So the bigger something weighs, the more friction that can have. So I want to do a couple different experiments here for changing a variable and seeing how friction depends on that variable. And a few of the things that we could change for this block, we could change how much this block weighs by simply adding blocks to it. So adding more mass on top of this will increase the force of gravity of the block. We could change the surface. You can see a very smooth surface here versus a rougher surface here. So that could change the force of friction. We could change the surface that it actually drags on. You can see that this is a very thin surface here, so small surface area, versus a larger surface area. So the two different surface areas could give us different frictions. And the last one we could do is speed. If you look here, it says that every single test must be pulled at a constant speed. If we pull at a steady speed, that should tell us something about our forces and tell us how we can actually measure this frictional force. Here's the Freebody diagram for our trials here by pulling the block at constant velocity. Forces you could identify would be force of gravity downwards, the normal force from the surface pushing back up. You've got the applied force or the tension from the force sensor, and combating that would be the frictional force. If we were talking about how the motion affects the forces, we know that if we're moving at constant velocity, we are not accelerating, so that must mean our forces must be balanced. And if that's the case, that means that gravity must cancel my support force up and down. And as long as I pull level, you can see that the tension has to equal the frictional force. So what our sensors can read is the tension in the rope, and the frictional force responds identically to that tension. So we're going to test each of our predictions and what comes up. So with those four things we can explore: the weight of the object, the smoothness of the object, the surface area of the object, and the speed at which we pull the object. I'd like you to make a prediction, and then I'm going to run through each of the scenarios and see if your prediction was right or not. You could say, if we pull the block with a faster constant velocity, so as velocity increases, I think the force of friction will increase, decrease, stay the same, and write some reasons down in your guided notes of why you think that is. So let's go through each trial here, and we'll talk about it. So I'm going to show you our experimental setup here. Our experimental setup is going to be a friction block, a force sensor attached to the spark. That's attached here to the computer with Spark View. I'm going to put this on pull positive for my force graph. When I hit play, it'll start recording the force that the force sensor records. And according to our Freebody diagram, you can see that the force in the force sensor, as long as I pull level with the plane, will equal my force of friction. I'm going to pull right here on the top of this computer card here. So it's a pretty rough surface already, and I'm going to pull this block across the surface, and we're going to see how the force of friction changes with each trial. In the beginning, to make everything pretty constant, I'm going to add a 500 gram mass to every single trial so that we have some type of weight so that some of those imperfections can grip onto each other and we can see what affects friction. Getting more mass on there, getting more speed or less speed, surface area or surface type. So I will pull with a nice steady speed all the way across, and you'll see the force graph respond accordingly. You got the friction block with a weight on it. We'll keep that weight on it for every single trial just so we have some type of mass besides just the wooden block. I make sure I zero my force sensor before each trial, and on the spark you should be able to watch the force change as time goes on. So there's my force graph. You can see there was no force. I started to pull it, peaked around 4 newtons, and then once I got it cruising, it kind of leveled off around 2.0 newtons. It did have a little drop off at the end there. It could be because I might have slowed down as I got closer to the edge here. A longer run might give us some better data. But let's try the next one. The next one is to increase the normal force. And to increase normal force, all you need to do is increase the weight. Force of gravity is now getting bigger. That means that a normal force must grow to respond so this doesn't fall through the table. So let's try this trial again and see if increasing the normal force increases the force of friction. I think that's pretty clear there. With more weight, the more force of gravity is pushing down, the more the normal force reacted and pushed back up. As the normal force increases, the force of friction increases as well. So if you want more friction, just increase your normal force, meaning add some weight to the car, and you'll have better grip in those snowy conditions. Now we'll do trial 2. I'm going to change the surface area. So the surface area, I'm going to go from having the wide surface to the narrower surface, pulling at the same steady speed. And I think that's pretty clear there. Changing the surface area actually had no effect. That purple line is the same as the red line there, so the force of gravity stayed the same whether I have the wide surface or the small surface. So surface area actually has no effect whatsoever. Let's try the side. Which side of the block causes more friction? The smooth wooden side or this seemingly rougher felt side? So we'll put the felt side down. And I think we can see again that with a rougher surface, this plastic, along with that felt, caused more friction. So depending on how rough your surface is, will depend on how strong your friction is. If we go back to the snowy road example, you want to have really good grip on your tires. You want to have extremely high hills and valleys that come down and grip the road to increase your friction. And it looks like we want to also put more people in your car, or some bags of kitty litter to weigh down your car and increase your force of friction. Last one to try is steady speed. So I'm going to pull this at a very slow steady speed, and I'll pull it at a very fast steady speed, and we'll see if speed is a factor in your force of friction. Slow trial. Fast trial. So looking at these speed trial runs, I did a slow trial, a medium trial, and a faster trial, and they're all hovering on average around 1.5 to 2 newtons. Speed actually has no effect on the force of friction. So depending on how you pull, as long as it's at steady speed, you'll always get the same force of friction. One other question that can be asked here is, does it take more force to get the object moving, or does it take more force to keep it in motion once you finally break the force of friction? And if you look, we have a high peak right up here around 10 newtons for this trial. That means that during this time, if you could watch the block while this was going on, that block was not moving. The force of friction was growing, and as soon as I reached about that 10 newton peak, the force of friction dropped off. That's when the interlocking of the block and the floor broke. So if you think of force of friction as hills and valleys interlocking, these hills and valleys were hitting each other. When I push on you, you must push back with an equal and opposite force. And when that ground pushed backwards, it kept us there. That's what we call static friction. When I got to that 10 newton peak, the ground couldn't handle it anymore, and those two snapped and flew past each other. So if these are hills and valleys, you can imagine the hills breaking apart on top of each other as the force of friction finally gives way. So now you can see when I was pulling at a steady pace, my average force in here was around 6 newtons. So it only took 6 newtons of force to maintain my motion, when it took 10 newtons of force to actually break it. Because once you're in motion, it's hard for those hills and valleys to interlock anymore. Your body wants to keep doing that. If you stop pulling, then all those hills and valleys will interact with each other and eventually slow you down enough that they can then snap back together. And that's how we create our kinetic friction. The kinetic friction is when those hills and valleys are in motion, and the static friction are when they're interlocked and before they even start to move. When you're static, you have no motion, and when you're kinetic meant motion for kinematics equations, that means you were moving. So you can see with the graph here, if you graph the friction versus the applied force, as you go along that orange line, the force of friction is increasing as you apply a force, but it finally gets to a peak. When you break that peak force, it drops down to a nice steady force as the object slides across the surface. So it does take more force to get it moving, but once it's in motion, you don't have to push as hard because inertia is kind of taken over. To solve for your force of friction, friction is fun. You can see little f for static friction equals mu. Mu is our rating or our coefficient of friction for a surface times our normal force. F equals mu times the normal force, or F mu n. So friction is always fun. And we'll be able to show you how fun it is when we have to worry about friction in our problems. That's for static friction. For kinetic friction, you just write it as F sub k, with mu k being the kinetic coefficient and normal force. You can see there's no surface area in this formula, and there's no velocity in this formula. All force of friction depends on is how rough the surface is, that's what the coefficient is, and how much the normal force responds to the force of gravity. In your book, there's a list of tables, and most problems will give you the coefficients of friction for different objects, but you can see like brass on steel is a 0.5 static value and a 0.4 kinetic value. Teflon on Teflon is a very low kinetic friction. You can see waxed skis on snow. People have rubbed every surface you can think of against each other to find the coefficients of friction, static and kinetic. Sometimes a problem will ask you to solve for that coefficient of friction, and other times you'll be given it, and it'll help you calculate your frictional force. And lastly, the bonus material here is you can see that there's a chemistry book on top of a physics book. And if you look at the chemistry book, we know that things are not perfectly smooth because of microscopic imperfections of those hills and valleys I talked about. So if I take one object and move it on top of another object, those hills and valleys interact with each other, and oh my goodness, you can see that eventually the physics book wears down the chemistry book and destroys it, because physics is harder than chemistry.